Hi everybody, this is lesson number 17 in the BC section of the course. This is about series. So in 16 we talked about sequence. A sequence is just a list of numbers that's generated using some formula, some equation, and plugging in whole numbers, no decimals, no fractions, no negatives, into, and also not zero, into the function to get the terms. So the difference between a sequence and a series is the sequence is the list of numbers and a series is what we get when we add up the numbers. So you use a sequence to generate a series. In the last section, we were interested in whether the sequence had a limit, like is there some number that these terms in the list are going to get closer and closer to, but they're never going to cross it. And now we're interested in the same thing with the series. So pay attention on the directions to whether you're being asked about the limit of a sequence or the limit of a series, because those are related, obviously, but not the same thing. We'll also use the terms converge and diverge, just like we did in the last one. So does this list of numbers added together diverge or converge? Well, if it converges, then that means that there's some number these can add up to, but they're never going to pass it. And I think I said that right. If it diverges, there's some number that these, no, I said it right the first time. Sorry, y'all. If it converges, then you can add and add and add and add and add, and there's going to be some number that they never pass. So you mean you can keep adding numbers infinitely and it never passes some specific value? I know that's really hard to wrap your head around, but that's exactly what happens. Not with all sequences, but sometimes. Or not with all series, but some of them. So if you guys look at this one, you can tell 2 to the n, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, da 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 da. The individual numbers in the list just get bigger and bigger and bigger. So when I start adding them up, I get a number and then I add a number to it and then I add an even bigger number. So the limit of the individual terms is infinity. Also the limit of the sums is infinity. So this will diverge. This next one, square root of 1 plus square root of 2 plus square root of 3 plus square root of 4 plus square root of 5. So even though that one's not growing as fast as 1, 2, 3, 4, 5, 6, 7, it's still growing and more and more and more and more. Square root of 49, and then eventually we get to square root of 64, which is even bigger, and then square root of 100, which is even bigger. So these terms get infinitely bigger. That means that the sum will get infinitely bigger. So this one also diverges. And these directions said that it's going to diverge. It asks you why. Well, the reason is because the limit of the individual terms is infinity. They get infinitely larger. So if you're constantly adding bigger and bigger numbers, you're going to get bigger and bigger answers. So that's divergent. This one, the cosine one, that one is going to oscillate. 1, negative 1, 1, negative 1, 1, negative 1, on and on and on. So an oscillating sequence is also, even if you're adding negative 1 and 1 and getting 0, but then you're adding 1 and then you're adding negative 1, and then you're adding 1 and you're adding negative 1. So there isn't some specific value that the limit is approaching. When you guys look at the next section, these are a little bit trickier sometimes. You have to be careful with these because I can look at this and I know that those numbers are going to get smaller and smaller and smaller, which is a sign that it might converge, but that's not going to guarantee that it will converge. So how do you tell if it will or it won't? Well, as we go through this unit, we're going to learn several different tests, but we don't know many of them yet. Like, well, none of them really. So what can I do to see if this is going to converge or diverge? Well, I can start making a list. The first number in this list would be a half. The next number would be 1/4. So when I add a half and a fourth, I get 3/4. The next one would be 1/8. The next one would be 1/16. So if I add 1/2 plus 1/4 plus 1/8 plus 1/16 together, I get 15/16. And at some point, maybe you see a pattern. So I know that these bottom numbers are 2 times 2 times 2 times 2. So they're 2 to the n. And then, hey, look, the top number is 1 less than that. So whatever the bottom number is, subtract 1 from it. So once I get to the point that I can write a function for the sum, I could do lots of things with this. What is the sum of, what is the sum of the first 53 terms? Well, if I don't have a formula, I would have to find all 53 terms and I would have to add them up. And that would take a really long time. But I can tell from this function, I don't know what the individual terms are, but I know what they're going to add up to because I have a formula for it. The other thing that we can do with this is what's going to happen with these terms individually. Are they getting bigger and bigger or smaller and smaller? Well, now I can do the limit as n approaches infinity, not of the individual terms, but of the sum of the terms. Is there something that these can add up to? If I could add all of these terms up from now to forever and ever, is there some number they're going to add up to? Well, that would be 2 to the infinity over 2 to the infinity, basically, which is 1. And you could maybe tell from this pattern, these numbers are getting closer and closer and closer to 1. So we're going to call that a name in a minute. But if you can find a pattern for the sums and find the limit of the sums, then you'd found the infinite sum. Okay, what about this one? Well, this one's a little bit trickier because of the way they wrote it. They wrote it as decimals, but if you look at it as fractions, it's a lot easier to see what the pattern is. The pattern for these terms, 9, 9 over 100, 9 over 1,000, they always have 9 on top, and the bottom is a power of 10. So I know what the individual terms are. We'll talk about why that's important in a minute. So what is the pattern if I add these all up? Well, 0.9. If I add the first two together, I get 0.99, 0.999, 0.9999. So if I look at this as I'm adding another 9 at the end, that's true, but it's not helpful. I need to look at this as how can I write an equation, some function that would give me this list of sums? Well, the bottom number is always a power of 10. So I've got 10, 10 squared, 10 cubed, 10 to the 4th. So the bottom is 10 to the n. And again, the top number is 1 less than that. So bottom number was 10, the top was 9. 199, 1,009.99. So here's our formula for the sum of the terms. These are the individual terms. This is what they all add up to. So what is the limit as n approaches infinity of the sum? So that would be 10 to the n over 10 to the n, which is 1. Okay, so what we're about to talk about is how does this work? Like, why does this one have an infinite sum and this one won't? So, I mean, I can tell because, I can look at the list of numbers and say, oh, they're getting bigger and bigger, or, oh, they're getting smaller and smaller. But that's not very mathematical. That's not good enough. So what we're going to talk about next is if you can find the pattern for the sums, awesome, do it. But what if you can't? Or what if you don't want to? Is there something else that we can do to tell if the sum will exist, if this series will converge, or if it will diverge? It all goes back to the individual terms, the pattern that's giving you the numbers in the list. So if I'm adding numbers that are bigger and bigger and bigger and bigger and bigger, then my sum is just going to get infinitely bigger. What if I'm adding numbers that are smaller and smaller and smaller and smaller? Okay, Well, that sounds better. But what if they're smaller and smaller and smaller and getting closer to 2? Well, then eventually I'm just adding plus 2, plus 2, plus 2, plus 2, plus 2, plus 2. And even though I'm just adding a small number, my sum is still going to keep increasing and it's never going to stop. So I started to say it's not about increasing or decreasing. It's not only about increasing or decreasing. Okay? Increasing just seems to not, like increasing toward infinity seems to not work. And decreasing, I don't know, maybe. But what if they're decreasing and getting closer and closer to 0? So the reason that works is at some point I'm still adding numbers, but I'm adding numbers that are so tiny, tiny, tiny that they're basically irrelevant. Like I'm adding 1/1 trillionth. Well, I mean, is that going to increase the answer? Technically, yeah, but by such a small amount that it really doesn't change anything. So this is called the nth term test, and you need to know it, and you need to know it by name. The nth term test says, if you can find the pattern for the terms in the list, not the sum, the terms, and they converge to, if the terms in the list converge to anything but 0, so if the limit of the sequence is infinity, no good. If the limit of the sequence is 2, no good. Then that tells us that the series, the sum, will keep increasing forever, which means it diverges. Okay, so what if it doesn't? What if it converges to 0? So the individual terms get smaller and smaller and smaller, so small that they're practically 0. Well, that tells us that the series could converge. Could. Not does, could. So that's one of the things that we can watch out for. These questions, for the most part for now, are going to ask you, does it diverge or could it converge? Those are my only choices right now. Either it will diverge or it might converge. No guarantees about the convergence part. So what are the questions going to look like? Well, they're going to look like this. Determine if this diverges or could converge. Well, in this pattern, what's my a sub n? A sub n is equal to 4 to the n. And the limit as n approaches infinity of 4 to the n, well, that would be 4 to the infinity power. That's just a really huge number. It doesn't matter big or small, really. What matters is 0 or not. And that is not 0. So that is going to diverge. What about 1 over n? Well, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, on and on and on. Those are getting smaller and smaller and smaller. So here's my function or my sequence. The limit of that sequence as n approaches infinity is 0, which tells us that it could converge. Not that it does, could. Actually, believe it or not, that one doesn't, but that's a different lesson. What about this one? Okay, so here's my sequence. And the limit of this sequence, oh wait, that would be infinity over infinity. What's that thing when I have limits and I get 0 over 0 or infinity over infinity? Oh, that's called L'Hopital's rule. So I can do the derivative of 3n, which is 3. I can do the derivative of n factorial, which is, I don't know. But what about the limit as n approaches infinity? So that's going to be 3 over a number. So, or 3 over some really big number. And when you do 3 divided by some really big number, you're going to get 0. So this sequence could converge. So how do you tell? You look at the sequence. You find the limit as n approaches infinity. If it's 0, then maybe it's okay. If it's not 0, then it's definitely not okay. This next example, these are called telescoping series, and they're kind of, I don't know, kind of cool, I guess. These are tricky. So you need to, the main thing about these is they're a special type of series that you need to recognize. And the thing that kind of makes them, I don't know, kind of stand out as something that's different is you have two terms and you're subtracting them. So when you have two or more, but usually two terms that are being subtracted, that's probably going to be a telescoping series. And here's what happens. You're going to get the list, you're going to get the function, and you're going to start plugging in numbers. So when I plug in 1, I get 1 minus a third. When I plug in 2, I get a half minus a fourth. When I plug in 3, I get a third minus a fifth. When I plug in 4, I get a fourth minus 1/6. And if I keep going on and on and on and on, I'm going to get 1 over n minus 1 over n plus 2. So this is why it's called telescoping. Look what happens with the terms. I had a minus 1/3, but then I also got a plus 1/3. I got a minus 1/4, and then later on I got a plus 1/4. So which ones am I going to be stuck with at the end of all this? Well, the 1 is not going to cancel out. There's no other 1. These numbers on the bottom just get bigger and bigger and bigger. So the 1 is still going to be there. The 1/3 and the 1/4 and eventually the 1/5 are all going to cancel out. But there was never a term that canceled out the 1/2. So what is going to be left of this series when I add all these terms together and a whole bunch of stuff cancels? The 1 and the 1/2 are still going to be there. And then whatever your last terms are still going to be there. So this, when it says find the n terms, this is what I want you guys to do. You have 2 of these on homework. I want to see that. Then, what is the limit? Well, the limit of the sum, not the individual terms, the limit of the sum, now that I have a pattern for the sum, as n gets really, really big, that's 0, that's 0, so the sum is 1.5. So if I could keep this going forever and ever and ever, then all of the terms in that list would add up to 1.5. So does that mean it converges or it diverges? Well, it converges because the limit exists. Could we have used the nth term test on this one? Yeah, we kind of could. I mean, that's going to be 1 over infinity minus 1 over infinity, so that's 0. So the nth term test told us that we would get an answer, but then figuring out the formula and finding the limit of the formula told us what the answer actually is. Okay, what about these? You have one, it's number 11, I think, on your homework that is very similar to this one. That does not look telescoping. So this one is not saying does it converge or diverge. It's telling you find the sum. Tell me what those are all going to add up to. Don't tell me that they're going to add up to something. Tell me what it is. So if you look at this pattern, you would get 4 over 3 plus 4 over 15 plus 4 over 35. Is there a pattern there? Maybe. I mean, it's not one that seems super obvious to me. The top's always 4, so I get that part. But what's the pattern? I'm kind of struggling with that one. So let's do the nth term test first. The limit of the terms, the individual terms, that would be 4 over a really big number, that's 0. So that tells us that this could converge. That's the nth term test. Again, though, that's not what the problem said. It said, okay, yeah, it's going to converge, but to what? So I got to figure out a way to figure out what these terms are all going to add up to. And let's see, 4 plus 1/3 would be 24 over 15. I'm sorry, 4/3 plus 4/15 would be 24 over 15. I mean, we could keep adding these together, but here's a trick, y'all. When you see a squared on bottom, I know it's been a while since we used partial fractions, but there's a chance this is going to factor, and if it factors, then we can turn it into partial fractions. So 4n squared minus 1 factors to 2n minus 1 and 2n plus 1. So what would make 2n plus 1 equal 0? Well, that would be negative a half. If I plug negative a half in and simplify it, then I get negative 2. So the 2n plus 1 gets negative 2 on top. If what would make 2n minus 1 equal 0? Positive a half. So now cover that one up and plug in a half. 2 times a half is 1, plus 1 is 2, 4 over 2 is 2. So the 2n minus 1 gets 2 on top. The 2n plus 1 gets negative 2 on top. And I'm going to flip the order of those so it looks like it's got minus in the middle. And there's your telescoping series. So now I took the original problem and I'm rewriting it. So we've got 2 over 2n minus 1 minus 2 over 2n plus 1. When I plug in 1, I get 2 minus 2/3. When I plug in 2, I get 2/3 minus 2/5. When I plug in 3, I get 2/5 minus 2/7. Keep going with this as long as you need to. But I can tell that this is going to be 2. The 2 is left because it never canceled out. And then I would have the 2 over 2n minus 1 minus 2 over 2n plus 1. That's the formula for the sum of however many terms I want. So now what is the limit as n approaches infinity of that sum? Well, if n is really, really big, this is practically 0. This is practically 0. So that tells me the limit is 2. And that's how these work. The hardest part sometimes is figuring out like what the formula is, or is there a formula? But we can talk about that in the homework, so I'll save that for a different video.